Hi everyone. So we're going to be looking at some new stuff today, but before we start, I thought it'd be good to have a refresher of what we already know. So I pulled up the Desmos activity, and this is what you all worked on in groups in class, and you would have come to this page at one point where we can make some conclusions that are helpful. When the derivative, right, the slope of the tangent line is positive, then our original function, which is represented by this red curve, should be increasing. Similarly, when the derivative is negative, then the function is decreasing, right? So that's been really helpful for us. We've been using this tool to find where we have min and max, or at least to classify whether or not we have a minimum or a maximum. Another conclusion is like these pages right here, which is a little more explicit. What I was already referring to, like this is how we can classify if we have a min or a max, is if we see the slope of the tangent line or the derivative change from positive to negative, right? That would be a maximum, because slope of the tangent line is positive before, then it's 0 at the max, and then it changes to negative after. And of course, minimum would be the opposite, because we have a negative slope hit 0, and then it becomes a positive slope. Okay. So this is what you've already figured out on your own. All right, so now what I want us to talk about is something different, and I just want to use this same activity so I can borrow the function and tangent line stuff. I want to move things around. So I'm going to just kind of move that off to the side a bit. We already know the general shape of a relative minimum. And we also know the general shape of a relative maximum. Take a moment to identify where you see a max or a min on this graph. Okay. Now, it would be super great if I could just have you annotate on the screen, since this is a recording, maybe just in your notes, sketch this function and then circle where you see a min or a max. Okay. So I'll give you a moment to do that. Okay, so if you were looking for a maximum, you probably found this location right here, specifically like that one point right at the top of the thing that looks like a hill, right? That's kind of how we've been, or I've been describing it in class. It's the top of a hill. And minima look like the point right at the bottom of a valley. Okay. All right. So we know that we can use the first derivative to prove for sure that a point we found is a min or a max, because we can look at the derivative before and after. Let's look at a minima. Okay, so we're going to use this min right here. And we know that beforehand, the slope of the tangent line is negative. But as I slide this, all of these slopes are negative, for sure, right? But they're not the same slope. Some of these slopes are much steeper than other slopes. And so we can see that as I slide closer and closer to the minimum, my negative slope values are becoming, in a sense, less and less negative, because we know that they are approaching 0. Right at the minimum, I'm going to have 0. So imagine if you're like at -4 or something, and you're getting closer and closer to 0, you're becoming less and less steep because your slope value is now maybe more like -0.5, which is definitely less negative. Okay, I'd rather owe 50 cents than owe $4, right? Because I owe less. Does that make sense? I'm hoping. So on this side, we're starting at like a large negative, and then it's becoming less negative until I hit the 0. What's happening to the slopes after the 0? What do we notice here? So we're 0. And we can already say for sure that our slope should be positive. That's something we already knew. Right? After a minimum, the derivative is positive. But I can see that it starts off as just like a not very steep, so a slightly positive number. And then it seems to be growing to a larger positive number. Okay, so let's write some of this down. We can see that the slopes are clearly changing. Right? It's not the same slope at all. It's definitely a steep negative. It's getting less negative. It hits 0, then it's a small positive, and then it becomes like a large positive. So it's becoming less negative and more positive. Okay. In other words, we could say that these slopes are increasing. Okay. So the slopes of the tangent lines are increasing around a minimum. Now, the very fact that the slopes of the tangent lines are changing, right? If something is changing, we should be able to find something that's responsible for that change, right? There should be something that measures that change. It's what we call the rate of change, right? So when we think of rate of change, I'm hoping that something's popping into our mind. And just in case, it might be helpful to have an example. If I had f of x equals x squared minus 3, and I wanted you to find the instantaneous rate of change at x equals 1, let's say, how would you do that? How would you find the instantaneous rate of change? If you remember, this is what the derivative represents. So we can take the derivative and then plug in 1. So the rate of change would be 2x, but at 1, we're going to get 2. So this is telling me that it's growing or changing at a rate of 2, because this function, f, is not staying the same. Right? The shape of this it's decreasing, and then it's increasing. Okay, so it's changing. That means that there is a derivative responsible for that change. So if I come back to this point now, we have my slopes of the tangent line, which is my first derivative. That's what slopes of the tangent lines mean. But that thing is changing. That thing is increasing. So just the fact that f prime is changing, I know that its derivative is responsible for that. I have the derivative of f prime. What's the derivative of my derivative called? It's the second derivative. I know that f double prime exists because that's how derivatives work, right? If your function is changing, a derivative is responsible for that, or a derivative is measuring that, right? That's how we know. The fact that f prime technically here was an increasing type of change. Increasing means that the derivative was positive. Just like how when f is increasing, f prime is positive. If I just like drop these down by a derivative level, it's the same thing. If f is increasing, f prime is positive. Let's plop extra derivatives on there. It should be the same. So I know that my second derivative all around the minimum and even at the minimum itself, because the minimum is right in the middle of this shape, this U shape, right? What looks like the bottom of a valley. This shape is what we call concave up. And that shape means the second derivative is positive. So same thing over here. You have like this U shape. That must mean f double prime is positive around here. In fact, all of this is technically part of there. So when f double prime is positive, that means our function f is concave up. So now that we kind of talked through a relative minimum, see if you can figure out similar things for the maximum, okay? I'm going to move this around here. I can see that my slope of the tangent line is positive, but it looks like it's becoming less positive as it gets closer and closer to 0. And then all of a sudden, the slopes become negative and they get steeper along this shape, right? Along this upside down U that makes it look like the top of the hill. That's where this is happening. It's a large positive, but then it's getting less positive and becoming more negative. Right? Less positive, more negative. So that means that the slopes of my tangent lines are changing, or specifically becoming more negative, decreasing. And if f prime is decreasing, that means my second derivative must be negative. So all around here, this little dot, this is what we call concave down, because it's facing downward, almost like a downward facing parabola. That's what concave down means. And this is where the second derivative is negative. So I'm gonna just kind of fill this in. I didn't really do that part. So an f double prime is negative. That means our original function is concave down. So this is some new information, and it's using the second derivative. And hopefully we can see that if you're trying to show that you have a minimum, right, if you found like, hey, there's a min right here, or there's a critical number right here, but you think it's a min, really all you have to show is that it's concave up, because that's what will give you that bottom of a valley shape. Right? So if x equals a is a critical number, then f double prime of a should be positive for a min. Similarly, oops, I missed it. So max means that we want this concave down shape. So if you have a critical number, you want to show that the second derivative is negative for a max, because that would get that shape, while min would need this shape. Okay. So this is hinting at, hey, maybe we could have another way to test things. Okay. This is getting us towards a second derivative test. So we have like another option now. Instead of just the first derivative, you could use the second derivative to find extrema. So we'll play with that in a little bit, but it's just kind of neat. What do you think about that? So there's one more thing that we should take note of here, and that's the fact that a function could have both a minimum and a maximum, just like this one does. It has a min, but then it seems to switch shapes so that I end up with a relative max, and then it switches shapes again to get me another min. So there's like moments of transition between this concave up and concave down. So I would like for you to, on your little sketch of this function in your notes, try to see if you could circle where it switches from concave up to concave down, or vice versa. So hopefully you're kind of looking somewhere here, and it looks like there's another one somewhere there, right? These are locations where it changes from concave up to concave down, or the other way, which means another way of phrasing that, instead of having to, you know, specifically have it concave down to concave up, or concave up to concave down. The word to just describe these shapes is concavity. So we have concavity. That's the way the curve is facing. And so your choices are up or down. So the places that we see there's a change in concavity, these are what we call like transition points, inflection points. We call them points of inflection. Inflection just means change, like when you have an inflection in your voice when you're speaking. It's because you're changing your tone, right? That's all inflection means. So point, let's not use orange, let's use pink. Point of inflection. It's just where the concavity changes. So that means it's in between up and down, right? It means it's in between, the second derivative is between negative and positive, or in between positive and negative. What do you think the second derivative is going to be when it's between positive and negative? If you are unsure, you can think of a number line. There is a gatekeeper between the negative world of numbers and the positive world of numbers. What are you going to have to cross through to change from one to the other? Definitely have to hit 0. So these are locations, right? Just for a moment, we have points where the second derivative is neither positive or negative, because we're not concave up or concave down, we're like switching. And so that means the second derivative is 0. So if you ever needed to find a point of inflection, you could try to find those by setting the second derivative to 0. These are potential locations. Now, it's not guaranteed because you still have to check that it changes on either side. So you want to test around where you think a point of inflection could be to show, oh yeah, F prime changes sign. Okay. We want to see F double prime change sign. And if it does, then you're like good to go. You found a point of inflection. If it doesn't, it's probably just a really, really, really flat part of the function. Like maybe you have like x to the 4th. That kind of like flattens out at 0. But we can see that it doesn't change concavity because all this is concave up, right? So you could have, situations where the second derivative shows up as 0, but it's not really a point of inflection. It's just like, it was just really, really flat. Because if it's really, really flat, that means like we're not registering any change. And so that's another thing, that when a derivative equals 0, it means you have a moment of no change. Right? That's just something you want to look out for. Okay. So make sure if you are looking for points of inflection, not only do you set the second derivative to 0, but you actually check that it changes sign. Okay. All right, so that was a lot of information. Let's just do a couple examples where we use this now. So if you remember, these were the 3 functions we were trying to find extrema for in class. I'd like to do a couple of them again and see if there's another way I can prove I have min or max. Okay, So we'll start with this first one. F of x equals x cubed minus 12x plus 5. So if I am trying to find extrema, locations of extrema, and then label if it's actually a min or a max, I know that I need my derivative to equal 0, because extrema mean that my derivative or my slope of the tangent line should be 0. So we're going to do that first. F prime of x. Set it to 0. And we should get x equals plus or minus 2. Now I need to just show that it's a min or a max. And so the way we did that before was with the first derivative test. And we tested around these critical numbers, because remember, these are critical numbers, places extrema might happen. And then we just like showed more information, using the first derivative test. But what I'm gonna do instead is try using my second derivative. So I'm gonna find f double prime, which is 6x. That's pretty nice. Okay. And I want to know what's happening at these numbers. So if I had a max, I know that my shape should look like this. Okay. At the maximum, I should be in the middle of a concave down part of the function. Okay. Like I should just be like right at the peak of that. So if I want concave down, I know that means my second derivative should end up being negative. That means I have a max. Versus a min, that should be concave up. So my second derivative would be positive. Now I'm going to have a min. So what I'm going to do is take my critical numbers. I don't need to test around them. I can just plug them straight into my second derivative and see what I get. So I'm going to do f double prime of 2, which is going to be 12. So that's clearly positive. And positive means I am concave up. So I'm just going to do the sketch because I like seeing the visual, because then I know for sure, oh yeah, f has a min at x equals 2. And then I could do the same thing with negative 2. I'm going to get negative 12, which is negative. So that's going to be concave down. So f will have a max at x equals negative 2. And this is the second derivative test. This is another way I could show the same work that we did together earlier. We used the first derivative test. We should have gotten the same exact results. I just did it a slightly different way now using my knowledge of concavity. All right, let's do number 2. I'm going to have you pause your screen. Try it yourself. Okay, so we're looking for the extrema. If you have not paused and done it yet, please do so. I want you to try and use the second derivative to prove if you have a min or a max. Then when you're ready, you can resume. Okay, so I want to first find my critical number. So I'm going to take my first derivative, set it to 0. Factor out of 5, I can see that x will end up being plus or minus 1. So these are my critical numbers. And in order to test, I'm going to take my second derivative. So f double prime is going to be 20x cubed. So f double prime of 1 is going to be 20. That's positive. So concave up is going to be a min. And f double prime of -1, that's going to be -20, which is negative. So concave down, that's going to be a max. So I can say f has a max at -1, and f has a min at 1. Ta-da! I feel like that saves some time because we're not really having to test all these in between values on the first derivative. I'm able to just go straight to the critical numbers. And the fact that I'm using the second derivative, it kind of ended up being a slightly simpler function. So the arithmetic was quick. So second derivative test can be very nice. All right, and then let's just do the last one. For simplicity's sake, I'm not going to explain everything. I'm just going to, do my work, because this trig stuff I know can trip some of us up if we don't know our unit circle well, but I did explain it in class. So if you're feeling a little iffy, maybe take some time to review unit circle stuff. But I won't do that here in this video. We're just going to get it. So pause, try it. You can resume when you're ready. Okay, so first, got to find the critical numbers. This is what I got. And now I'm going to test those critical numbers by plugging them into my second derivative. So I have to find f double prime, which should be square root of 2 sine. And now f double prime of pi over 4. That's going to be rad 2 times sine of pi over 4, but sine of pi over 4 is really just 1 over rad 2. So these are going to multiply together, and I'm going to get 1, which is positive. So it's going to be concave up. And then f double prime of 7 pi over 4 should be square root of 2 sine of 7 pi over 4. That's below the axis. If you think of your unit circle, 7 pi over 4, pi over 4. So 7 pi over 4, the sine value, which is the vertical, is actually going to be negative 1 over rad 2. So it's going to be negative 1, which is clearly negative, so it's going to be concave down. So it looks like this will be the location of a max, and this will be the location of a min. So I can say f has, I'm just going to shorten it. I'm going to say min at x equals pi over 4, and max at x equals 7 pi over 4. And then if you remember our discussion in class, essentially, this is just 2 solutions. And we know that there's going to be an infinite number because I can just rotate around and around and around, but I should always land in the same exact spot. Right? Like if I rotate around again to 9 pi over 4, it's going to also be a minimum because it's the same thing. So I can just plop on plus or minus 2 pi k onto my answers. Yeah. All right, so this is just, you know, the same problems that we did, but now you can see another way to find and label extrema. If you have any questions, please make note of them, and you can bring them to student hours, or you can ask me next time in class, okay? But thank you for watching, and I will see you next time.